Okay, first of all, so I want to talk in a little bit more detail about temperature. Because where we're really headed in this unit is we want to start talking about the so-called gas laws and the Albedo gas law. Before we can do that, we got to get a more detailed understanding of temperature. All right? Now, I've already mentioned this before, but I want to go into a little bit more detail about it. That is that temperature is proportional to the average kinetic energy of the particles. So this here is the average kinetic energy. It's really like the root mean squared or something like that, but you can think about it as the average kinetic energy, and then this is the temperature. All right? And let me show you what that means in with a graph. If we look at a graph and we plot the kinetic energy, we plot the kinetic energy versus the number of particles. Okay, so this is like a histogram, kind of like what we saw when we were talking about entropy and W. We might get something like this. And that would be the Boltzmann distribution. So if you watched the video that I made where I went online, I had this little applet and there were the particles, and you saw that the distribution of energies was approaching this blue line. This would be the blue line, and that is the so-called Boltzmann distribution. So what you have here, this is the number of particles. No. That's the caffeine. So the number of particles is on the y-axis, and the kinetic energy is on the x-axis. So what do we got here? We got most of the particles right in here. This would be the average, right? And so what we're saying is, as we increase the temperature, the average goes up. The average slides to the right. It doesn't mean that all the particles have the same energy. They don't. Remember, that would be a very low entropy situation if all the particles had the same entropy. What happens if you start with all the particles with the same energy? They will naturally spread it out randomly so that you get something like this. This is the natural distribution according to the second law. So what happens as we heat it up? As we heat it up, we get something more like this. Okay? So this right here is a low temperature system, and the red line is a high temperature system. High T. So as we slide this to the right, now two things happened here when I raised the temperature. I'm trying to draw this as if there were the same number of particles in the system, low temp and high temp. Not only does the average slide to the right, so the average moved to the right, but the other thing that happened is the particles, the whole distribution got kind of squashed. So there's a much wider range of temperatures. We still have some low energy particles down here, even though we're at a high energy. But of course we have a lot more at a higher energy up here. Now what happens, what are some of the implications of this picture? Implications of the fact that the temperatures, the energies are not all the same, they're spread out. So some have very low energy, some have very high energy. One is for evaporation. Okay, let's say that this was a liquid. So, for example, if the blue curve is a liquid, let's say it's water. we can say this: a certain minimum energy is required for evaporation to occur. And this goes back to intermolecular forces. If we picture the surface of water like this, and here's some water molecules. Remember that the water molecules are held to each other by hydrogen bonds. So we have here hydrogen bonds holding water molecules to each other. They hold the molecules in the liquid state. So, in order to evaporate, you've got to get enough energy to break those bonds. So let's picture a water molecule that has freed itself. In order for a water molecule to break free at the surface, this is evaporation right here. In order for that to happen, that molecule has to have enough energy to break the hydrogen bonds. And basically what might happen, you could picture it like this. Let's say a molecule gets hit from below by another water molecule. So a water molecule comes up and hits it from below. If it hits it with enough energy, it might break the bonds, the hydrogen bonds. We're not talking about the water molecule's actual covalent bonds breaking. They don't break. The water molecule stays intact. We're talking about the hydrogen bonds. If it gets hit with sufficient energy, then it might evaporate. Okay, let's look back at our graph. Let's say, for example, that this is the minimum energy to evaporate. That is that in order for the molecule to break free of the surface of the water, to break free, it has to have this amount of energy. That means that at any given time in the water sample, a small portion of the water molecules have enough energy to evaporate. So this, we could say, is the portion of molecules that could evaporate. This is why evaporation happens at all temperatures, not just the boiling temperature. So let's just say this. What's that? Go back up. So this is why evaporation happens at all temperatures, because at all temperatures you've got at least a small portion, even if it's just way up here in the upper tail end. You've got at least a small portion that have enough energy to break free of the surface, even at very low temperatures, even at near freezing. You've got a little bit. Now, what happened with our experiment? Remember, one of our biggest errors in our heating curve experiment was that we were losing a lot of water to evaporation toward the top of our temperature. As we approached, say, 90 degrees and above, we started to lose a lot of water to evaporation. Why? Because this curve kept shifting to the right. Now look, this line right here, the minimum energy to evaporate never changes. That's determined by the strength of the hydrogen bonds. So what happens as you continue to raise the temperature of the water, you continue to shift this distribution to the right, you end up with most of the water molecules having enough energy to escape. Okay? Or at least a larger portion. So the implication of this is that at a given temperature, there will be some water molecules at least there will be some molecules that can escape. And then, as you increase the temperature, more and more will have the minimum energy. Okay, so one of the implications of these curves is that they explain why a little bit of evaporation happens even at room temperature. If I fill this with water and let it sit on the counter, it will dry out eventually. Slowly it'll lose water until eventually it's totally dried out. Okay? How can that be if it's not at the boiling temperature? Here's the reason. There's always at least a little bit of water molecules at a given temperature, even room temperature, that have enough energy to escape the surface. Okay, questions so far? So the main message at this point is not all the molecules or particles at a given temperature have the same energy, and that has implications. All right? One of which is some of them will be able to escape the liquid state into a gaseous state, even though the boiling point has not been reached. Now this is important. We talk about the boiling point as the transition between a liquid and a gas, right? What I'm telling you now is there's a little bit of fuzziness to that. Water evaporates even at less than the boiling point. So what is boiling? What is so special about boiling? What is boil? Yes?
It's when all of the molecules gain the minimum energy.
Essentially. The question was, is it when all the molecules gain the minimum energy? Essentially, that's it. Is that 100% true? I'm not entirely sure. If that were, you would think they would instantaneously all just flash into a vapor. But I mean, that's a good question of what would this curve look like for boiling. I'm going to have to get back to you on that. Here's the way that the official definition of boiling. It's when the vapor pressure equals the ambient pressure. Now, what we got to do here is we've got to unpack this a little bit because it's got some terms in there that you're probably not familiar with. So let's unpack this. First of all, pressure. Let's make sure we're all on the same page with what pressure is. Pressure is a force per unit area. It's a force per area. So if you take a certain surface area and you apply a certain force, that's a pressure. Now when we talk about gases, so gas pressure. We talk about gas pressure. Gas pressure is caused by molecules hitting a surface. hitting the surface. That means they're applying force. So instead of something like, right now I'm applying pressure to the floor. I'm standing on the floor, and so I'm applying a force to a certain area, whatever area I'm standing on. But in terms of gases, what's happening is this. We've got, say, a wall or something, and the gas particles are just hitting it like this. So the gas particles are hitting the wall and pushing on it. So the gas particles hitting some kind of a surface and pushing on it. So typically what we think about with gases is you might have a container. And let's say that we had a piston here. So this piston can slide up and down. And we put a gas in here. We've got particles then that are going to be bouncing off the walls and hitting this thing. Particles of gas strike the walls, and the piston, exerting a pressure. Okay, now let me show you what I'm talking about here. This is just a syringe, and I put a little cap on it to seal it. As I push on this syringe, it gets harder and harder for me to push on it because I'm compressing the gas, right? What's really happening is there's a whole bunch of molecules in there that I can't see because they're too small. But as I'm pushing on this, it's literally the molecules pushing back. Now, they're not obviously pushing back like this. They're literally hitting the sides of the walls at like 1,000 meters per second. And there's so many of them that I actually feel it as a major force, and I can't even push against it at some point. Those molecules are exerting so much force when they're hitting this. You don't believe me. You believe me? You believe me that there's a bunch of tiny invisible molecules in here that are hitting this piston so hard that I can't push in beyond a certain point? You believe that? A bunch of little molecules, the whole sample of molecules together, that whole sample of molecules in there probably weighs less than, oh my goodness, like 10,000th of a gram. And yet you're saying that 10,000th of a gram of molecules is, how can that be? The force that I'm feeling right now is much, much greater than a 10,000th of a gram. How can something that small and that light exert such a great force on this piston? Who can tell me? Yes? Okay, you're right. That's why it increases, because the area is getting smaller and there's still the same number of molecules. That's why the force increases. But how can something so small exert such a great force that some big strapping person like me can't fight against it?
Use the force.
Jordan.
Increase the density.
Okay, it is increasing the density. Now, of course, they're still widely separated, even at this point. Those molecules are not anywhere near each other. I mean, yeah. Okay, so that's true. They will hit the sides more often. That's true. What I'm getting at here is just that you have to consider the speed. They're moving very fast. Like I said, maybe 1,000 meters per second. And they're hitting the walls so fast that even though they're small, they have a lot of energy. Right? So speed makes a big difference. I mean, think about bullets. A typical bullet is about that big, right? And yet it does a large amount of damage. Why? Because it's going so darn fast. So a bullet does its damage because it has tremendous kinetic energy. Even though it has a small mass, it has tremendous kinetic energy. And that energy is transmitted to the thing that it hits, and that's what does the damage. All right, so this is what we're talking about when we mean pressure. All right, now what do we mean when we say, let's do this one first, and vapor pressure you'll see tonight in the video. Let's talk about ambient pressure. Ambient pressure is just the pressure in the environment. We would say, like in this picture I just drew, it would be the pressure outside the piston. Pressure outside the piston. So for example, outside the piston. Now, most commonly, ambient pressure is the same as atmospheric pressure. So, most commonly, ambient pressure is atmospheric pressure. So let's talk a little bit about atmospheric pressure. Standard atmospheric pressure. You know, we talk about standard room temperature being like 25 degrees C. There's something called standard atmospheric pressure. It doesn't mean that that's always where atmospheric pressure is. It just means that they had to set a standard. They said, whenever we say standard atmospheric pressure, here's what we're talking about.
Like room temperature.
Just like room temp, yeah, like 25 degrees C. And here it is 1 atm, which is equal to 14.7 pounds per square inch, which is equal to 760 millimeters of mercury. What's that? I'll get to that. So first of all, before I explain why what millimeters of mercury means, let's look at what the source of this pressure is. Here's the Earth, and here's you. Okay? And basically, you are always under this pressure from the air. Right? So air has mass. If you swing your hand like this, you can feel the air, right? We are essentially like air fish. We're always walking around under this ocean of air,
Floundering
right?
around.
Now birds can fly through it, right? But anyway, there's this ocean of air over the top of us all the time. And it's always pressing down on us. Why is that fun?
Wait, what was it what I said about floundering around?
I don't know.
Or are we
Well,
just working this?
All right, so basically, here's the atmosphere on top of you. Picture it like this. There is a huge column of air right now pushing down on you that goes from the top of your head all the way to the outer atmosphere. Now, the atmosphere obviously is just a blanket of gases that's being held, that's around the Earth. The Earth is shrouded in this kind of blanket of gases. Here's what we're saying. On every square inch of your head, 14.7 pounds of air is over every square inch of your head. 14.7 pounds is over every square inch of your head. Okay? Now, here's a kind of a weird thing. Let's say that, so here's your hand, okay? Hold out your hand. So if you're holding out your hand, how many square inches is your hand? Maybe like, say 4 by 6, 24. Let's say my hand is 24 square inches. That's probably a little high, but if my hand is 24 square inches, 24 inches squared, how much weight is on my hand right now? If I'm holding it out like this, according to what I'm saying here, if I'm right, 24 square inches times 14.7, that's 353 pounds. So right now, there's 353 pounds on my hand, 353 pounds of air, and it extends all the way up to the atmosphere. But there's a ceiling. So that brings us to my next question. How come I don't feel like there's 350 pounds of air on my hands? What's that? Well, besides that. What's that? Yeah.
Because your hand pushes back.
Well, I would feel it. If I had 350 pound weight on my hand, I would definitely feel it, right? Of course, I would just toss it off like a, okay? But if, what I'm saying is this, what's pushing up down here? There's also air into here, right? And listen, air is squishy, right? So if there's a bunch of air, so the same amount of air that's above my hand is also above this point right here, right? And what's it doing there? It's just pushing down on the air below, right? So around my hand, there's air pushing down on the air below it, which is squishing it all down and compressing it, and it's squishing back up under my hand with the same amount of force. So I don't feel it, right? I don't feel it because it's pushing down. Let me show you one thing before we go. I'll get a better one to show you. That's how suction cups work. What you do with a suction cup is you push air out from behind the suction cup, and now the only force acting on this is a force pushing it against the wall. And if this is say this was 6 square inches, that would be 60, about 84 pounds pushing on this thing against the wall. So to pull it off, I've got to exert 84 pounds of force. Why? Because I pushed out the air that was behind it. See, if I just hold this here, it doesn't hold against the wall because there's air behind it pushing out with the same force. But as soon as I remove the air, from between these, it suddenly becomes hard to separate them, even for a brute like myself. Right? So, if suddenly all the stuff inside your body was sucked out so that you were just like a hollow shell, your body would crush like a what? What's something that crushes? Like an empty eggshell.
Like a bottle, like a plastic bottle in an airplane.
All right, anyway, so this is pressure. And basically,
The thing isn't.
so let's zoom in here on this hand because this is an important point. Okay, this is an important point. Here's your hand. Okay, whoops. Yep, just a second. Drawing a hand. Okay, so there's a hand. Now, what happened? All right. Now, there is your hand. So here's what I'm saying. If I've got 352 pounds pushing down here, that's because there's 14.7 on every square inch. Right? But what I'm saying is, if the same pressure is pushing down right here on this level, then that means all the air is getting squished and it's pushing up with 14.7 pounds per square inch. Okay, so one of the rules about a fluid like air or water is that if you're at the same elevation in the fluid system, then the pressure's the same everywhere at that point. Okay, homework, vapor pressure vids, and mini quiz. I don't remember how many it is. There's a couple of them, I guess.